Right, it's time to look at surds and what are surds. Now, this is a section of the syllabus, comes from chapter 3, indices and surds. Now, if you look across the top at all the topics we've done this year, yeah, look at that, we've done a lot of work. And you come up against, oh, 2 topics ago, indices. You know, we were looking at things like, what happens when you take x squared and raise it to the power of -2, and this was indices. Now, this section, indices and surds, it's the same chapter, it's chapter 3, and we picked that up at about 3F or whatever. Indices was the back end of it. We're now going to start from the start of the section, which is the surds section, and they're related. They're related. I'll show you how. A half power. We didn't look at fractional indices, but x to the power of 1/2 is the square root of x. Now we can go into why that's the case. If you take x to the half and multiply by x to the half, what do? You've got same base. So what do you do with the powers? You add them together, don't you? So you say, well, that's equal to x to the power of half plus half is 1. That's equal to x. So x to the half times x to the half is x. So what multiplied by itself gives x? What do I know about this? And hopefully you realize that the square root of x, when you square it, you get x. If you've got the square root of x multiplied by itself, you get x. Think about it. Square root of 4, square that, you get 4. So the square root and the squared are opposites of each other. So it's like taking a number, multiplying by 2, dividing by 2. Multiplication and division are the opposite of each other. So what you get if you multiply and divide by the same number, you get back to where you started. So if I square root 4 and then I square it, I'll be back to 4. Or if I do the opposite, if I square 4 and then I square root it, I'll be back to 4 again. So there's operations in mathematics, all operations have got an opposite. So that's how it fits into this section. X to the power of a half equals the square root of x. So I'm just going to put a little frame around this because that's kind of a little bit of background or a bit of context. We haven't actually studied fractional powers. We delicately steered you away from that. We did negative powers, and you probably remember, just a little recap here, that x to the power of -2, that became x to the power of 2 when it went underneath in the fraction. If you switched it around, or 1 over x to the -2 was, I'll put that on top. Sorry, I'll put that on top. It becomes x to the power of +2 over 1, or just x to the power of 2. So we did negative powers. We didn't look at fractional powers. But fractional powers are square roots. Now, surds, that's what surds are. Surds are square roots. So surds are irrational numbers. So if we have a look at the real the number system, I'm going to take you through. Did you know there was a number system? Well, there is. A system of numbers. Now, the number system is like so. You've got real numbers that are real, or you've got numbers that are not real, complex, sometimes called imaginary numbers. You're not going to have to worry about that unless you get into some serious top-end, heavy-duty maths. You'll end up as you are at the moment in the real number system. Everything you've looked at has been a real number, but real numbers can be broken down further into rational numbers, rational and irrational numbers. Okay, irrational numbers, these are numbers that can be written as a fraction, can be written a over b, where a and b are integers, right? Where a, b are integers. That's real numbers. Okay, so 6 is a real number because that's 6 over 1. 2/3, that's a real number. All these fractions, all the decimals that, 0.1, that's a tenth, that's a real number. Sorry, a rational number. They're all real, but irrational numbers can't be written like this. So a feature of rational numbers is that when they're written as decimals, they'll either terminate or recur. Irrationals, when they're written as decimals, they go on forever in no pattern whatsoever. So irrationals are things like pi, another letter, Greek letter E, that you won't have come across yet, and surds. Surds are irrational. Surds are the square root of numbers. So surds are square root of 2, square root of 3, square root of 5. Okay, and how do these numbers come up, and why do we bother with them? Well, if we've got, let's look at a right angle triangle here, 1 unit by 2 units. Right, there's 1 unit there, that's 2 units there. And if we want to have a look at the length of the hypotenuse of that, okay, that's a right angle triangle. We know from Pythagoras, don't we, that that this squared plus this squared equals this squared. So if you square this side here, that's 2 squared. You know, you put a square on that side, you've done this. Right, now that's the area of that square plus the area of that square will equal the area of the square that sits on the hypotenuse. Right, so this is 4, isn't it? The area there is 4, the area there is 1. So this has to be area 5, so that means this side has to be square root 5. That length there is square root 5. So what is that? What is a square root of 5? Where does that fit in? So yeah, we start, well, okay, so it's on the number line. Now if we start to think about where these things exist on the number line, if that's 0, 1, 2, 3, right, then square root of 5, we know it's somewhere between, like 2 is the square root of 4, isn't it? And 3 is the square root of 9, so it'll be in here somewhere, square root of 5. We don't know exactly where, but it's in there somewhere. But it's irrational, which means that when you turn square root of 5 into a decimal, if you wanted to go and do that, then you would see that the decimal digits go on forever. Look at this. I'll turn that into a decimal. 2.23607. That's only 5 decimal places. That's not so interesting, but it goes on forever. If we wrote 2.23607, we're not able to write this in a recurring way. If you've got a third, you know that recurs. The 3 recurs. All 0. I think this is 1/6. All fractions, all rational numbers have recurring decimals or terminating decimals. Irrationals have decimals that go on forever. You know about pi. Yeah, this guy here, 3.14159, known to something like 60 billion decimal places. There is no pattern. So irrational numbers, surds, are part of that subset of numbers. So they're square roots of numbers that can't be reduced. So square root of 4 is not a surd, because square root of 4 is 2. That's rational. That's a rational number. Okay, so there's a little bit of a preamble about surds and what they are. Let's start to have a look at different types of surds. You might know also that this here is the cube root. So that means what cubes to 8? Well, then the answer there is 2. Well, what about the fourth root? The fourth root is written like so. So if you've got a little number in here, that's the root you're taking. If it was fourth root of 81, well, that would be 3, because 3 to the power of 4 equals 81. So this is how it works. If there's no number written in there, we assume square root, and so we answer it that way. So what number squares to 25? Well, the answer is 5. So I know you've done some square root stuff before. I'm just recapping a bit of it. Okay, some rules. Let's have a look at some rules before we get on and do some questions. So we know that the square root of x, when you square it, you'll get x. We know that the square root of xy, right, we can split this up. And that's a really useful one, that one. Split it up. So that's, we can look at an example here. The square root of 36, which we know to be 6, we can split it up to be square root of 9 times the square root of 4, because 9 fours are 36. Alright, if we didn't know that was the case, that's 3 by 2, that's 6. So you can see that works. You split it down like that. If I got the square root of 20, I can write that as the square root of 4 times the square root of 5. Now I've chosen 4 because that's a square number. Now that's equal to square root of 4 is 2. Square root of 5 can't be reduced. So what I've done there is I've simplified square root of 20 by using one of its square factors, and I'm using this surd rule here that I can split up. So square root of 20 equals the square root of 4 by the square root of 5, which is 2 root 5. So that's how you simplify surds. All right, let's move on with some more rules. There's a fraction. There's a nice little fraction rule here. Square root of x over y equals, I can split them up like so. Yeah, so I've got, let's say, the square root of a quarter. Right, that's the square root of 1 over the square root of 4. So you can split your numerator and denominator up, and you might be able to simplify your surd that way. Okay, let's have a look at some examples to finish off this particular YouTube. Examples. Right, let's have a look here. So simplify the following. Simplify the following. Now see if you can answer these questions before me. If you can, that'd be great. Simplify the following. Okay, let's have a look. Square root of 32. So we're going to simplify square root of 32. What we're looking for is we're looking for a factor of 32 that's a square number. So what goes into 32? So this is what I'm thinking. I know my factors are 32, or 1 and 32, 2 and 16. Whoa, 16 is a square number. Brilliant. Square root of 16 times the square root of 2. 16 twos are 32. I can write it like this. The benefit of that is that square root of 16 is 4. I don't write the times sign. In future, I'm just going to go straight to 4 root 2. I've simplified root 32 to 4 root 2 using its square factor of 16. Let's see if you can do the second one. 3 root 200. There's a number out the front. Don't be put off by that. That's just equal to 3 times. Let's find these two square roots such that we use a square factor of 200. Now 200's got a square factor of 100, hasn't it? 100's a square number. 3 times the square root of 100 is 10. Times the square root of 2. Now I just have to multiply 3 by 10 to simplify it to 30 root 2. Okay, let's keep going. 5 square root of 40 over 6. Okay, let's simplify this. Now again, I'm going to concentrate on this surd. It's 40, I've got 4 and 10. That looks good. That's a square. That's 5 times square root of 4. That's 5 times 2, which is 10 root 10 over 6. You see what I did there? 5 times 2 is 10. Now the 10 and the 6 can be reduced to 5 and 3. So the simplest form is 5 root 10 over 3. We go to square root of 75 over 9. I'm going to use this fraction rule here to split that up to the square root of 75 over square root of 9. That square root of 75 I can write as 25 by 3. Square root of 9 is just equal to 3. Square root of 25 is 5. So I've got 5 root 3 over 3. And that is my simplified answer. Excuse me. Expresses a complete surd. So I can write 2 root 5. I can write that as the square root. So this is sort of unsimplifying, if you like. So I can write square root of 2 root 5 as a complete surd as the square root of 20. Okay, sometimes we want to be able to do that. What's the 7 root 2 as a complete surd? Root 49 times root 2. That's square root of 98. That's sometimes going to be useful for us as well. Okay, that's enough of an intro, I think, for surds. We can have a look at exercise 3A when we're in class tomorrow. I'll see you then.